Hi, so today we are going to create a custom IP inside Vivado. So as you can see, I'm using Vivado 2023. So we're going to create a project, maybe select a library, and I can write custom IP as name of the project. So I'm using pink Z2 board. You can select your board. So in this project, I will be just using the peripherals of this pink Z2 board, which is the switches, buttons, and LEDs using a custom IP. So first of all, what we are going to do is we need to create an IP. So we have to go here in Tools, Create and Package a new IP. Next, so we are just going to create the AXI peripheral IP. Next, you give a name for your IP. I would give it pink peripheral, and I'll choose a custom folder IP repo. So yeah, here you can select the number of registers that you're currently using or you need to use. I need even one register is enough because we're just reading and the LED, we're just reading the switches and push buttons, and we just need to write to LEDs. So even one register is enough, but the minimum of number of registers is 4, so we will just select 4 and then next. So we're going to edit the IP. The first thing is we will come to file group. Here, these two files are the main files that we have to edit. So here, as you can see, this is the protocol for AXI4-Lite IP, which is written by Xilinx. So here we can just modify some of the code and add our own ports and logics. So here, as you can see, user to add ports here. So I need 3 ports, one for switches, one for LEDs, and one for push buttons. So I would write pink LED, pink LED. This is an output of the type is standard logic vector. And since my pink Z2 is having 4 LEDs, I will write the 3 down to 0. And pink switch. This is an input of the type is standard logic vector. Because pink Z2 is having only 2 switches, so I will be defining as 1 down to 0. And pink push buttons, this is also of the type N, standard logic vector. My pink Z board is also having 4 push buttons. I will define it as 3 down to 0. So you save it. Now you have to define how you're going to access these peripherals. When you come down, here is the signal generation and all the other data types that are required for the AXI4-Lite implementation. So we come down. Here you can see this is the implementation for writing to the registers that we have previously selected. As you remember, we have selected to have 4 registers. So this process is controlling how we are writing to these 4 registers. Suppose if you're having a signal that has to be triggered, then you can add it into this process. But now since we need to read the push buttons on switches, so we have to find the read process. So this one is the read process. Select and read logic generation. So we need to you can decide which registers you need to use, but I'm using slave register number 0. So when I'm reading register number 0, I have to read the value for switches and push buttons and push buttons. But as you can see, this read data out, it's a 32-bit register. So 32-bit register is push buttons. We have 4 push buttons plus 2 for the switches. 4 plus 2 is 6. So we have to add 2 zeros to make it 8, and then the rest of the zeros. So X means hexadecimal, and each 0 we put in here means 4 zeros. So 8, then you have to add 6 more zeros. 1, 2, 3, 4, 5, 6. So 6 into 4 is 24. 24 plus 8 is equal to 32. So both the right and left side is having 32 bits. So the logic is to implement the when I am reading the register number 0 on the first 2-bit, I'm reading the switch 0 and switch 1, and then the push buttons from push button 0 to 3. We said that we have only 4 push buttons on the pin Z2 developing board. The next thing is we have to write the logic for writing to the LEDs. So you can write to the LEDs like this: a P LED is equal to slave reg 0, 3 down to 0. So if I write to slave register 0, so the last 4-bit is going to be routed to the LEDs. Okay, for just a simple IP to use the LEDs and switches, if you want to make a custom IP, then this is the whole implementation. So we have implemented the read logic, and if there's anything to be done for the write logic, we will edit it in this process. But here, since we are not implementing any write logic, we don't have anything yet right here in read logic. So we have added push buttons. So we have to add this one also on the sensitivity list. So copy slave register 0 is not here anymore, so we can replace this one, and also the switch. So push button, switch, and also the LED. If I write to slave register number 0, so the last 4-bit is going to be routed to the LED. So we can save it. Yeah, here we can see that there's another top level file. This one is this file. This is a sub file of this one. So whatever changes to the ports that we're bringing to this file, we need to add those changes to this peripheral also. So this is the architecture implementation of this. So here, these ports should be exactly the same as the ports defined here. So remember that we have added three ports here, two input and one output. So we have to add these things also here. So these ports. We also need to add these ports on the top file to be able to map them from the sub file to this top file. So I'm adding this one here also. This is, remember, this is the top file. I've added this one, but maybe it's also possible to have the same names for the top file and the sub file, but it is better to change the name. For example, I can just add a U just for user ping switch. I can save it. The next step is to map these two ports together. So remember, we have defined this component. This component is defined here, and down there it is mapped. So I'm adding the ports here, but this has to be mapped, so we don't need this definition. And also the port defined here should be mapped to this user. And maybe you can have a U. Okay, so we have implemented the logic in this file. We have added the port. We have added the port here in the top file. We have port mapped them. So that's all. So you don't need to write any logic here. We have written all the logic here, which was this implementation of this LED, which is the output. So we save both the files. So merge changes. Another thing is also there is a make file here. Yeah, this is the make file, but in this make file you have to bring some changes. As you can see, it is using some header files, C files, and object files, which are in some folders, and the version of the make in which this version of Vivado is using is a little different than the version of the make software which is used for software development kit from Xilinx, which is Vitis. So we need to add a macro here which is called wildcard to all these three definitions. Yeah, so it is done. All files are saved. Now we have to package it. Merge changes, port and interface. We can see that we have an UP LED, which is out, 3 bits, switches, push buttons. All the ports are defined here. You can check it before you proceed. So those are the addressing and memory, customization ID. So you have one IP, which is having the switches, push buttons, and clock reset, and output is the UP LED. So we're going to review and package. So we acknowledge that this IP has been modified, and then we package it. Yeah, we have made the IP. Now we have to make the block diagram, and we have to use the processor which will drive this IP and write software, so that we'll be able to write the software and control this IP. So I'll make a block design. This block design, I will call it just pink peripheral design. So this peripheral design, first of all, we can add a processor, and ping Z2 is having Zynq 7020, so we can add that software inside our design. And now we have to add the IP that we have just generated. So add pink peripheral. We have added the board. We have added our IP. What we can do is this processor is having a lot of components, and sometimes it is like that we don't need all the components. If I run the block automation, it's just for the processing of this processor. So I will automate so that all the things inside the processors or processor is initialized. As we can see here in the peripheral I/O, we have Ethernet, USB, SD card, and all these things. It's not all of them are used. For example, for this case, we don't need Ethernet, we don't need USB, we don't need SD card. For if you want, you can deselect it and don't use it. If you need it, then you can select it. So, but as of now, I will keep it like this because it doesn't make any harm. So there's also this designer assistance if you run connection automation. So this is going to just automate the connection between this processor and the IP that we have just generated. So I'm clicking on that one. Everything is okay. So now we have created our block design. And as you can see, this pink peripheral, it's made on the FPGA fabric. And this processor, Zynq processor, it's a hard processor on FPGA silicon. So in order that this processor be able to talk to this FPGA, it's not possible to directly talk. So there is an AXI interconnect. This AXI interconnect is a bridge between this processor and FPGA fabric logic that is talking to each other. We said that we are having these ports, this UP switch, UP push buttons, UP LED. So we need to make them as external port. So just right click, make external. Here also makes external, make external. As you can see, the name of this port is UP switch 0, UP push button 0, UP LED 0. Xilinx is adding underscore 0 to this port. because it's thinking that we might have another component of the same type, so there should be a difference between, but as you can see now we don't have it, so we're just going to remove this underscore 0. So by the way, you can edit by the properties of it here. I'll remove this one also. LED, remove. Okay. So now what you can do is you validate your design to see if everything is okay. Yeah, validation successful, and there are no errors or critical warnings in this design. Then we go to sources and see that this file, it's a board design, but board design, it's not possible to synthesize it. So in order to be able to synthesize it, we are just going to create an HDL wrapper. For creating an HDL wrapper, you right click on the file and you select create HDL wrapper. Let Vivado manage wrapper and auto update. You select OK. It takes a little time. Yeah, so the HDL wrapper is created. As you can see, this HDL wrapper represents this block design, and this is in VHDL. All the ports defined. Okay, so after this, we need to synthesize our design. But for synthesis, we need to add a constraint file. You have to tell Vivado like this switch, push buttons, and LED on which pins these signals are located, or these ports are located. So I'll add constraint file, so you can get a master constraint file from every vendor that you're having the board from. For example, I'm having a ping Z2, so there's a master constraint file from ping Z2 vendor. So I have it. So I'm copying constraint file into project. I don't edit the original file. I'm just getting a copy of it into my project, and then finish. Constraint. As you can see, the constraint file is here. So as you could see, there's this switches. We did not use RGB LEDs. We just used simple LEDs and these push buttons. So switches, we need to uncomment. LEDs, uncomment. And buttons, uncomment. Save it. Yeah. Here for switches, there are two switches. As you can see the diagram, there are two switches, 1, 2, 0. The name is up switch. So I have to change the name here, up switch. Yeah. And LED is UP LED. UP LED, and buttons is UP push B. UP push B. So these are all the things that you have to edit, and everything is done. So now that we have done everything, we should start our synthesis. We say run synthesis, and this process is going to take a little time. Okay, so now we can see that the synthesis is completed. So we have to run the implementation. So we say just okay, run implementation. Yeah, so we can say open implemented design to see if everything is okay. So you can see LED, UP push button, UP switches. So there is nothing wrong with it. We can say generate bitstream. Yeah, bitstream generation is also completed. So as you can see, bitstream generation complete. Now we can we have made a custom hardware, so we can export it. You go to File, Export, Export Hardware. Next, include bitstream. So we want our hardware generated with the bitstream generated. Next, so pink peripheral design wrapper. Next, finish. Now we have created our custom hardware. So here, as you can see, there is this pink purple design wrapper. This is a Xilinx software architecture. This is a Xilinx system architecture file. You can use this file to create platforms for your software design. So in this video, I'm just going to make a small software just to show you that the custom hardware that we have made, it's we can write program for it, and we can also check that it's working. The directory that we're going to write the software, so custom IP is our project folder. So I'm going to create a new folder called Vitis workspace. Vitis is the platform that, Vitis is the software development kit for Vivado from Xilinx. So we can select folder, launch. So first of all, we have made a custom hardware. So in order to be able to write software, first of all, we need to create a platform so that we can write our application on top of it. So I'm writing the name of the platform as pink peripherals platform. Here you need to select your XSF file that you've exported from Vivado. So you go to Browse, Pink Peripheral Design Wrapper. This generate boot component, I'm taking this one because I'm not going to generate boot components. But in cases where you are using SD card to, when you're just turning on your FPGA board, then it should boot this application, then you can take this generate boot components. But as of now, I'm not taking that. Yeah, so we have made the platform, and we can check that if our IP is there. So we can go to board support packages and check here in the drivers. So there should be this pink peripherals. Yeah, here as you can see, our IP is there. So we will write the application on top. As you can see it here, it says out of date. So we need to build it. So we build it. So I tried to build the Vitis platform, but it didn't work. The problem was that the wildcard, it has to be a D here. Sorry for the inconvenience. You have to make it like this. I came back to Vivado, corrected this one. You save it, and then package it again to warning. These are just because the port has been edited, that's why there's into warning. So the package, yes. So we have to update this IP to this done. So upgrade selected, generate. Yeah, then you have to run the synthesis, implementation, and bitstream generation all over again. So I am going to do it now. As you can see now, all the IPs and everything is updated. So now synthesis and implementation is out of date. It's just updating itself. Then we have to run the synthesis, implementation, and bitstream generation. But you can just directly click on bitstream generation. So it's going to automatically first run the synthesis and then implementation and then the bitstream generation. You can see synthesis is out of date. Okay to launch synthesis implementation first. Yes. So, okay. Now it's going to run the synthesis implementation and then bitstream generation. So now the bitstream generation is completed. So okay, so everything is done. So we have to export it again. Export hardware, including the bitstream. And this time maybe we can design number 2. Next, and then finish. Okay. As you can see, it is still out of date. I can update the hardware here. Just update hardware specification. Browse. The second design here. Open. Okay. Is updated. I will check the board support package that it's having the or IP. Yeah, pink peripherals. Now we should be able to build the platform. So this is still out of date. It means that it's not built. So I'll say build. Yeah, as you can see now it is not out of date. So it means it is already built. So I'll make the application on top of this platform. So you click file and create new application project. Next, so I will select the platform as pink peripherals platform. Next, and then you have to give a name, pink peripherals application. So now you can see that this is a standalone domain application, and we are using the processor ARM Cortex-9 and core number 0 because this pink Z2 is having a processor with 2 cores. So now we're using the core number 0. Next. So now here you can write your software application. I'll write the software application in C. So let's say hello world in C. Yeah. So this is our project. We go to sources. This is the hello world.c software. I can right click on it and rename it, maybe to something more better. Pink peripheral app. Yeah, these are some generic information, we don't need it. This is for the UART. We need this one for connecting to the board. So now you have to write C application. Inside Vitis, by generating and compiling the platform, it's giving us as a file that I have to include it in our C file. That's called xparameters.h, and this xparameter.h is containing the data regarding the registers that are used in our custom IP. So I can right click and go to the definition, open declaration. So here all the registers are defined, but we have to find the custom IP address that we have created. So the name was ping peripherals, so I will just search for ping, and as you can see, it is found. Ping peripherals. This is our IP, and this is the register. So I'll copy this one. So this is an IP, this is an address. Okay, I have to read from this address and write from this address. So I will define a macro here. Hash define reach k as. Since we're reading and writing from this address, we don't want any optimization of the C compiler. That's why we need to define it as volatile, unsigned, integer. And by the way, I'm just declaring a pointer to this address. And then this address is having some range, and in between these ranges there are 4 registers. You remember that we have selected that this IP should have 4 registers. So it is this base address plus 4. So the ranges are in 4. For example, if you want to access the register number 0, so this is the base address. If you want to access the register number 1, so you have to add 4 into this base address, then you will get the register number 1 and so on. So I'll just make it as plus 4 into k, because we can register access register k just by using this macro. But as you can see, this is still a pointer to this address, and we don't want a pointer, we want a value. So I can just dereference it. And later here I'm just defining some macros for some parameters that are used inside the C programming for the user. So maybe like I'm getting some commands from the user, so I am defining command length as 64, and I will define one function called void print help, and I'm just printing something to the user just as helping. So this printf, it's for using the Xilinx print function. I'm not going to use, I'm just going to use the printf function. So maybe if the user is entering H, then it should show the help menu. And if the user is printing X, then it has to quit the program. And if the user is entering LED, to turn on the LEDs. And print if the user is using SW to turn on the switches. and if the user is entering PB to maybe not to turn on, to read the switches, and also here to read the push button states. Yeah. Since we're going to get the commands from the user in string, I'm going to need the string library also. And so I will remove these things, define some parameters that are used for our program. So I'll just create a terminate variable that's currently 0. I'll use and make the command that we'll be getting from the user command line, and then unsigned int xdata. This xdata will be used to exchange information between the registers. So if I'm writing any values to the register, or if I'm reading any values to the register, so I will use this xdata. I will use one do while loop, and this loop will be running until terminate is equal to 0. So I will print this one just to show that the program is ready. And since the program is going to expect null termination, so I'm going to flush it to std out. Now I'll get the command from the user, and this is important. We need to get a safe. You need to use a save function for getting the string from the user, and for that case, I'm going to use fgets to the command length of command length of stdin. Now here, based on the operating systems, when the user is entering some commands, at the end there will be some null termination or carriage return a new line. But it really depends on the operating system. So we need to fix that one. Maybe we can use a function, or I'll do it here on the spot. I'll just define the pointer, character pointer, and when I'm getting the command from the user, I'll terminate it with a null termination, and then I will remove the carriage return and new line, and I will say that current pointer is equal to the command, and until the value of the command pointer is not equal to the carriage, the null termination, I will loop. And I will do if the value of the ch pointer is equal to new line, or it is equal to the carriage return and here in the new line, or even if it is equal to the null termination, then the value of ch pointer is equal to the null termination, because we only need null termination. We don't need any carriage return and new line. And also, if it is in this case, it has to break and plus plus. So this whole code, it's just going to remove the carriage return and the new line from the command that user is entering. Now that we got the command from the user, we have to read and write specific values to and from the board. So we have added the string library here, comparing it with if string compare of command with h. If it is comparing with h, then I will simply print the help function. Else if this string compare, if command is equal to h, then I will print help. Else if command is equal to x, then I will make terminate equal to 1. And when I make terminate equal to 1, then the whole loop is going to stop. Else if str compare command, if it is LED, then I will get the value from the user and write it to the board. As of now, I will just print help LED implementation. Else if string compare of command and SW, then it has to return the state of that switches. So as of now, I'll just write switch implementation. Else if str compare of command with PB, I'll just return the state of push buttons. As of now, I will just print PB implementation. So else if none of these commands are entered, but length of the command is greater than 0, it means that the user has entered anything else, then it should say printf invalid entry. So as of now, we can just check this code to see if it is working properly. So for this, you have to connect your FPGA board to your computer. So you have to compile this program just to see that if it's working. I'm compiling the application. So as you can see, it's compiled. It's giving me a warning that X data is not used because this is unused variable. So as of now, we can ignore it safely. Yeah. Now I have to connect the UART. I've connected my Zynq, my Pink Z2 to my computer, and you have to use a UART software which is called Kitty. Yeah. I've made the settings and all these things, but you can do it like this. That the baud rate is 115200, and mine is on COM4, so it is a serial. So I'm using COM4 and with the speed of 115200. You start it. Sorry, I have to turn on my board. And it's on. So you start it, and then you have to run your application. You right click on it, run as GDB. For some reason it's not working. I've checked it with my board, and the reason is that I'm using this fget function. For some reason it's not working. That's why I need to write another function. Let's get char. So for that I'm using another function, void get my, maybe my get command. The entry would be command with the size. So I will define one character, and I will make an integer. I will loop, and I will get up to we have to find that the command length is 64, so I will loop until 64. Initially I will for I is equal to 0, I less than size minus 1, I plus plus. So I will use ch is equal to get char. So this get char is a function which gets the character from the user using through uart, and we can compare it, and we can process it also on the spot. If character is equal to new line, or character is equal to character or new line, then I will say that the character is equal to null termination, because we want to remove character and null termination. And then for each of the character that we are getting from the uart, I'll put it inside command. So command I is equal to character. And then if for the case that the user doesn't enter anything, then I will just make the command I equal to the null termination. Then we can save it. So instead of using this fget, I can use my get command function. So maybe I can comment it, and my get command of cmd and cmd length. Okay, so I can compile it once again. As you can see, it is getting compiled, and then we can run it. But yeah, I can compile it here and run it. Run. So as of now, you can see that keyboard is not working. Maybe we can check the problem. Sometimes in connection, when using the terminal, you have to make the line discipline option as local echo force on, and local line editing also force on. And then you have to come to session, COM4 11.200, and maybe we can give them this name, this setting a name as pink per and save it. And then you can start this being per. Then if you enter, yeah, it's working. So I can run my application here. Yeah, it's here. Yeah, I know there is some problem with this function. So if character is equal to the null termination, then we have to break it. Otherwise, it's not going to work. Build it and then run it again. Yeah. As you can see now, it's working. If I press H, then it's showing me the all the help menu buttons. If I write LED, then it is giving me LED implementation. If I write software, then it's giving me software implementation, and PB, the push button implementation. So as of now, I'm going to write X just to close it, and then it is closed. So as of now, I can just make the program a little bit better. First, if the user is running the program, then it should print help. And also at the end, if the minute is done, then it should give me a message that program run successfully. So in our project, we have this IP repo and HDL. I'm just seeing here. As you can see, this is the Vivado file that we already done. So switch, there are two switches. Maybe first we can implement this LED. In LED implementation, I will just print if I'll get the value from the user. So I will write, please enter the value to be written to the LEDs. And since we're having only 4 LEDs, we can write them from 0 until 15. Print if the values should be in between 0 to 15. Then I'll get the command cmd linked. I get the command, and then I have to get it to fix data. So I will say that using sysconnect, because I'm getting a character from the user, and I have to extract the number from that character using sysconnect. So as you can see that this LED, and then I'll get from the command a number to the address of X data. Then I'll say if X data is, I should only write the values from 0 until 15. If you write the values above 15, it will also write, but it's not going to be displayed because there's only 4 LEDs. So if X data is greater than 0, and X data is so it can also accept 0, and X data is less than 16, then I will write the value to the register 0, else printf the values are out of range. So I can say that range 0 is equal to x that. So this is the way that we can write the values to the range data. So I just compile it again. Wow, range 0. Unsigned int volatile and sorry, this is unsynced. Unsigned int. So yeah, undefined reference to print help. It should be undefined reference to print help. It's in line 60. Print if help. So that shouldn't be like that. It's just print help. Yeah, it's compiling, and now I can run it again. So this is my UART. Run. Yeah, as you can see, it's running again. And so I can write help. This is the help menu. So I will write software implementation, push button implementation. These are not implemented yet. So I will write LED. Yeah. So as you can see, these values should be written. And suppose I'm writing the value of 5. The value of 5 is written to the LED, and I can show you using the board. So it's like this. So now as you can see, the value 5 has been written to the ping Z board. Now I'll make it 0 again. So help LED, and I will write the value 0 to it. So at 0, all LEDs will be off. Yeah, these all LEDs are off. And if I write the number, for example, 15, all the LEDs should be on. As you can see, all LEDs are on. And LED, for example, 7. Yeah. So the next step is we're going to implement the reading of the switches and push buttons. So as of now, we can close this one. Program run successfully. So in the software implementation, for the switches, as you can see here, our switches are the last. How many bits did it have? So we have 2 switches. So I have to read the register number 0. So I will write X data is reg number 0, but X data is containing the 32-bit itself. So I don't want the 32-bit. So I will write, I need only the first two LSB bits. X data is equal to X data and 0x. So the 2-bit is 3. 0x3 means 0x3 means 1100. So I just need to read the first 2-bit, and others are all zeros, and then I can print it. The state of the switches are, I want to show it in hexadecimal format as X and X data. So build it again. Unused variable switch pointer. Okay, this is also unused, so I can comment it. We build it again. Second. Sorry. X data is equal to. So we can build it, and then we run it. Help. Okay, so in software, now the state is 0. I can show you in the board. As you can see, these are the two switches, and both of them are in 0 and 0. So if that's why it is showing 0 here, and if I change it this one to 1, so 0 1, it means 1. And again, I can see software, now it is 1. And if I change it again, this one 0 and this one to 1, there should be 2. Software, and this is 2. If I change both of them, software switches, so now it is 3. Then again update it, both of them tested 0, so now it is going to show me 0. So this is the implementation part for the switches. Now we're going to implement for the push buttons. So push button is also the same thing, except we need to process the X data. So as we can see, X data, we need to discard these two first bit and then take the next 4 bits. So X data is, first I will discard the 2 bits by just right shifting it, and then I will get the 4 bits. So 4 bits, it should be like this, and this is equal to, I'm sorry, this is not 33, this is 3, and this means 15, and 15 means F. Okay, 0x F, and the state of the switch is this one. So I will just compile it. So as you can see, it is already compiled, and then I will run it. So as you can see, it's already run. Help. I'll just see the push buttons. PB implementation. Oh, sorry, it's in the wrong place. I have to add all these things in PB implementation. So build and run it again. Help. So PB state is 0. Now it is 4 because it's the third LSB. So this is bit number 0, 1, 2. And if I'm keeping this one as pressed, then it will be 4. If I'm keeping this one pressed, then it will show me 8 PB. So this is one last time for showing the implementation. As you can see now, LEDs are 0, switches are also in 0, and push buttons are also in 0. So if I'm writing anything LED, I'm writing the value of 3. So this is writing the value of 3. And what are the switches status? Both of them are 0. I'm changing this one to 3. Soft switches, now it is 3. And also for the push buttons, I'll keep it pressed. I'll try to. So as you can see, now the state of the LEDs are 3. I'm just making it 0. So it is 0 now. And I'll just read the set of the switches. So it is 3. As you can see, both of them are on. So I will change it to 1 switch. And the state of the switches are 1. And now 0 switches are 1. I will also show the push buttons because I have to keep it pressed and at the same time enter push buttons. Now I am keeping it pressed and 8. This is the fourth push button. Now the third push button, it should show me 4. Now the second push button, it should show me 2. And now the first push button, it should show me 1. If I'm keeping the first 2 pressed, then it should show me 3. Now the second 2, it should show me 6. Now the last 2 bit I'm keeping it pressed, then it should show me 12, which is C. Now you can see this is just a simple IP for reading and writing the registers, but we have used the peripherals, push buttons, switches, and LEDs just to read the states and write to LEDs. So thank you so much. This was a fun program, and see you next time. So program done successfully. Bye.